Good afternoon. Thanks for the introduction. In my talk today, I want to focus on management and monitoring of GPU clusters. So with the increasing number of GPU clusters and with the increased size of these GPU clusters, this topic will be getting more and more important. I want to cover the following topics here: a short introduction into management and monitoring of GPU clusters, an overview about the tools NVIDIA is providing and third-party vendors are providing, GPU management and control. I want to introduce GPU modes, persistence modes, InfoROM things. GPU power management is getting more and more important to set power limits, to set application clocks, to set the so-called GPU operations mode, and last but not least, GPU job scheduling. So scheduling to specific GPUs. Hardware locality is a big topic today, and a short summary. So from the requirements point of view, management and monitoring of a GPU cluster has a lot of similar requirements to CPU clusters, of course, ease of installation or integration into deployment tools. In my talk, I would like to cover more GPU-specific things, for instance, monitoring GPU states or abilities to change the GPU states, the power management, as I mentioned, and also the scheduling of GPU jobs in order to get a high utilization of the whole cluster. From the tool points of view, NVIDIA is providing so-called NVML library, NVIDIA Management Library. It's an C API, and on top of this is an NVIDIA SMI command line tool, which I would like to introduce a little bit later. And for the NVML library, we also have bindings for Python and for Perl. You can download this NVML library from this website, developer.nvidia.com Tesla Deployment Kit. What is the NVML library? It's a C-based interface for monitoring and management of various states of the NVIDIA GPUs. So the intention is to integrate this NVML library into third-party applications. So we don't want to provide a general cluster management and monitoring tool. We want to provide tools for the management and for the monitoring of GPUs, which will be integrated into third-party applications. It's thread safe. There are different calls in this NVIDIA management library for the initialization or for the cleanup, query methods for system or for the device, control methods, device commands, event handling, error reporting methods, and NVIDIA ML library is supported on Tesla and on the Quattro product line. Here's an example for a C program with the NVML calls. So you have to initialize the NVML library first here. Then you can call different NVML calls, in this case NVML system get driver version, which gives you the current installed GPU driver version. You can get the device count for this system, and here you go via loop and get all the device names, and at the end you have to shut down the NVML. Compiling this NVML test program gives you as an output the driver version, found two devices, and the listing devices are two K20M systems in this case. As I mentioned before, we also providing bindings for Python and for Perl, which we support and which we update with each CUDA release. And you can download these bindings from the links which are provided on this slide. Also, two examples here for the Python version. In this case, same approach like for the C version, NVML init, NVML device get count. Here, in this example, you request the get the clock info for the SM, for the streaming multiprocessor. You also request the max clock for the memory and power usage as a call, shutdown, and you see here the output of this small test program written in Python. So current clock speed in megahertz, 324, memory clock speed in megahertz, 2.6 gigahertz, and the power usage. Similar example as a Perl version. So also here, init, get driver version, get device count, and get memory info and shut down so that you have all the information available. So it's very easy to integrate this NVML version into scripts like Perl scripts or Python scripts or in C programs. One of the applications which we are providing and which is based on this NVML library is the NVIDIA SMI. It's a cross-platform command line tool, so it's available on Linux, on Mac OS, and also on Windows. So intention is for interactive use and also for automation. We are providing with a special switch here with a command line option -X an output in XML format, which you can use for something like you want to manage. Here are two examples. NVIDIA-SMI-Q queries all the attributes for the GPUs which are installed in the system, or you can also use NVIDIA SMI in a loop, which gives you every 120 seconds in this example an output what's going on the GPU. We are providing this NVML library in order to integrate this in third-party tools like Ganglia. So there is a Ganglia monitoring plugin for GPUs, which you can download from this site, and also a plugin, sensor plugin for GPUs for Nagios and Icinga, based on this NVML Perl binding, which was written by Georg Schönberger, and you can download this from this website, Thomas Krenn, from the Thomas Krenn AG. Other examples for the integration of NVML into third-party tools are the Bright Cluster Manager and also the HP Cluster Management Utility, CMU. Another tool which we are providing is the so-called nvidia-healthmon. So it's a diagnostic tool for a quick health check. It helps you to remedy software and system configuration problems, and there are currently a special feature set here integrated, for instance, a basic CUDA and NVML sanity check, or a diagnosis of GPU failures, or a check for conflicting drivers, or poorly seated GPUs, etc. Also a bandwidth test in order to check if the GPUs are providing the expected bandwidth. If you are using this nvidia-healthmon, you have to be careful in conjunction with the job scheduler, because nvidia-healthmon also creates a CUDA context, and if the GPUs are running in exclusive mode, normally the job scheduler thinks that he is the only application who is using this GPU. So there's some coordination needed between the job scheduler and the nvidia-healthmon tool. The nvidia-healthmon is controllable via a config file. It can be configured, and here you see sample config.ini file. You have a global section here and section for dedicated GPUs. Bandwidth 1 or bandwidth min gives you a warning or an error message when this bandwidth is not reached. So there are several use cases for the nvidia-healthmon tool. For instance, you can integrate this healthmon script into cluster scheduler prologue or epilogues. It's designed to integrate into third-party tools, of course. If you have provisioned a node, you can run nvidia-healthmon in order to check if this node is running well, or you can run it directly manually. Here you see an output of this nvidia-healthmon tool. It's an extended run with a -e option. So global tests check for blacklisted drivers, check for NVML and CUDA sanity, gives you the number of GPUs which are installed in the system, and then you run several tests on the specific GPUs, and you get here an output about, for instance, memory bandwidth or the PCI Express bandwidth and the memory which is allocated. So it's a very nice tool to use it, as mentioned, in schedulers, in resource managers, scripts, or in node checkers, like many users, many sites have installed. Out-of-band management is, of course, also a requirement for the management of GPU clusters. We are providing an out-of-band API, which is quite similar to the NVML API. It can be integrated into the lights-out management. It minimizes performance jitter. It provides a subset of the NVML functionality, for instance, checking ECC or checking the power draw temperature and something like that. It requires system vendor integration because it has to be integrated with normally with a BMC board, which is integrated into the nodes. GPU management and control. Talking about this topic, of course, one of the most important points is to know about the so-called compute modes. The compute mode controls whether individual or multiple compute applications can run on this GPU. So there's a default mode where multiple host threads can use the device at the same time, or there's an exclusive thread mode. Only one host thread can use the device. Prohibited compute mode, no host thread can use the device, or the exclusive process compute mode. Normally, the clusters are running in exclusive process mode. And you have to be aware that NVIDIA SMI-C settings do not persist across reboots or driver installs. So you have to set this compute mode at every boot in a boot script or something like this. There's also a so-called persistence mode for Linux only, and this persistent mode causes the driver to maintain a persistent connection to the GPU. Otherwise, there's no client like an X Windows or whatever is running on the server, the driver will be unloaded, and this causes longer startup times and so on. So that in most cases, customers are setting the GPUs into persistence mode. Also here, not preserved between reboots, you have to set the persistence mode in the boot scripts. If you administer a large number of GPUs, of course, unique number is needed, and in the last, or from the last driver versions, from the driver version 3 or 4, we are providing tools or calls which gives you the so-called UUID. So you can use this UUID in order to identify specific GPUs. Also, NVIDIA SMI-L gives you the UUID of the GPUs. InfoROM, we also introduced this small persistent store of configuration and state data for the GPU. And it's good that you have this store. You can put in a configuration checksum on this InfoROM, and it makes it very easy to verify that two GPUs have the same configuration. So, for instance, if you have two GPUs also in different nodes, GPU 0 has ECC mode set to off, GPU 1 has a ECC mode set to on, then the InfoROM configuration checksum will give you a failure and says it does not match this checksums between the two GPUs. This checksum verification is also exposed in the nvidia-healthmon script, but you can use it also in your own scripts by calling the NVML device validate InfoROM call. Power management. The GPUs have the ability to regulate the power draw and terminals via active clock and voltage management. Normally this is done automatically, but as a user or system administrator, you can also direct this manually in some cases. For instance, you can set the power limit or set fixed maximum clocks, or you can also query for performance limiting factors with a new Kepler GPU, which has a much more enhanced support for power management. Here's an example to set a power limit for a GPU. NVIDIA SMI-PL 85 sets the power limit to 85 watts. So the clock of the streaming multiprocessors and also the memory clock will be set down, and it gives you lower performance, of course, but you will still be live in this power limit. It's also possible to set application clocks on the new Kepler generation, which means you can set the clocks to a maximum for compute and graphics applications. You can query supported clock pairs with the NVIDIA SMI-Q-D supported clocks, and you can set clocks for dedicated applications. For instance, if you want to power down the streaming multiprocessor clocks and to get higher memory clock, you can set it with the NVIDIA SMI-AC script, and at the end you can reset the clocks. So we heard this morning in the talk from IBM about energy-aware scheduling, and with this kind of tools or of settings, you can integrate the power management into your scheduling management. In this case, it was LSF this morning. The application clocks will be overwritten by out-of-spec events, for instance, by power or by the temperature. If the temperature is too high, and you can query the reasons why the clock does not fit with your settings. NVIDIA SMI-Q has here some outputs about the clock throttle reasons, and in this case the GPU was idling, but you get also the information if the clock is limited by software-defined clocks or limited by software power limits set with a minus power limit, or limited by hardware limiters, for instance, the temperature. It's quite useful to have this output in order to understand the GPU performance. For instance, if you have some problems with your temperature inside the nodes, then you will get this feedback here with the output about the clock throttle reasons. GPU operations mode is also new to the Kepler architecture, and you can set the operation mode for GK10, 110 based K20 or K20X GPUs. It's interesting. Here you have three modes, all on, compute, and low double precision. And default mode is a compute mode, so running only compute tasks, but you can change the compute mode in order to switch on the graphics capabilities of the K20 and K20X, so that you have a remote visualization cluster with the K20 and K20X. But of course, with all on, with the switched on graphics capabilities, you will consume a little bit more power. Job scheduling as a last topic in my presentation. More or less all job scheduler and resource management systems are supporting GPU scheduling, so Slurm, LSF, PBS, the grid engine from Univar or from the open source, or also the adaptive computing MOAB Torque. What are the requirements for GPUs scheduling? For instance, of course, maximize the utilization of the GPU resources in the cluster. Another requirement is the handling of different GPU configurations, so different types of GPUs, different numbers of GPUs in a node. And what's more and more important is the mapping of the GPU resources depending on the hardware topology. In order to get better performance, for instance, the CPU, GPU pinning is important, or also GPU peer-to-peer communication via GPU Direct is very important to have the right combination of GPUs which are communicating. Also, the integration of features like the CUDA, so-called CUDA proxy is important, and you need to have the ability to run prolog or epilogue scripts like we have seen with the nvidia-healthmon script. More or less all the scheduling systems are using the CUDA visible devices in order to select the right GPU in a system when you have more than one GPU in a system integrated. CUDA visible devices allows you to hide GPUs for a job. So you can, for instance, set CUDA visible devices to 0. Then only the first GPU will be exposed, and the second GPU, which is also installed in the system, will be hidden. Or you can switch the index of the GPUs. So, for instance, CUDA visible devices set to 1,0 will expose the first two physical devices, but swaps the order of their device indices. It allows a batch system and the resource manager to control specific devices, GPU devices. Hardware topology-aware scheduling is important. I used here as an example the HVlog utility, and the HVlog utility discovers the server topology and provides you an API to select the right CPU-GPU combination. So for my tests, I used the pre-version, pre-release of this 1.7 release, which supports also the NVML. And for instance, ls topo -v gives you the following output here. You see the link speed here, in this case, 8 gigabytes per second. You see the vendor, the PCI slot, where the GPU sits on. And also there are some other informations here about the GPU model, or also the UUID of the GPU. If you use HWlog with the Cairo graphics toolkit, or if you compile this with this Cairo graphics toolkit, you can also produce nice pictures with the ls topo -- output format. You see here two sockets, one socket, CPU socket, the other CPU socket, and you see here the NVML 0, so the first GPU, the second GPU, and you get also an overview about the PCI bandwidth, which we have also seen in the text output. Here is a skeleton for an MPI application in order to use the right or the best hardware topology, the best combination of CPU, GPU setting. So at first, you read the environment variables in order to get the local MPI ranks. You call the HWlog topology, and you set the CUDA set device, and you bind the CPU to this GPU device, and then you can call your normal MPI application stuff with the MPI in it, with your MPI computations, MPI finalize, and at the end you can delete the CUDA context with a CUDA set device reset. So this gives you a skeleton to have this hardware topology in mind, and you can bind the GPU to the best fitting CPU. In summary, with the increasing number of large GPU clusters, the management and monitoring is getting more and more important. We as NVIDIA are providing management and monitoring tools, APIs like this NVML library, which is used by NVIDIA tools, NVIDIA SMI, for instance, and third-party tools. Power management features provide reliable performance and power savings in some cases, and the topology-aware scheduling will increase performance significant. And we hope that this kind of topology awareness will also go or will be integrated into job schedulers. So we are working with some partners on the integration. But this is a very hot topic. That's all for today. I believe I'm in time and I'm open for questions. Thanks.